as we've talked about in class, a graph is not determined by the way we sketch it. We could sketch it in several ways probably, depending on the graph. It's not the way it's sketched, but rather the vertices it has and how they are connected by the edges. And so there's several ways to capture that, the essence of a graph, the nature of a graph. The picture might display it for us and make it easy to understand, but we need other representations to be able to work with it. And for example, to code one into a computer, you would definitely need some sort of way to represent it. So one way to do it is called an adjacency list, where we just list the vertices and then aside that list the vertices that they are adjacent to. So as an example, we'll just draw a graph here that looks like this perhaps, and maybe has these edges here and these edges here, like so. So let me call this A, B, C, D, E, and F, like so. And here we'd have the vertex and adjacent vertices. So A, B, C, D, E, F. And A is adjacent to B and E. B is adjacent to A, C, F. C is adjacent to B and F. D is adjacent to E and F. E is adjacent to ADF. And F is adjacent to everything but A, B, C, D, E, like so. There is redundancy here because once we've gotten past A, there's no point in listing A again. In these two places here, that carries the same information we have here. Once we get past B, there's no point in listing B again. Once we get past C, there's no point in listing C, etc. So there really isn't any point in some of the things that we have listed there, but that's usually written with all of those in there. I guess one of my points is that there might be simpler ways you could do it. We will talk about one here where it too contains some redundancy, but it is a nice convenient way to display them, a graph, and also is useful in computations. This has some obvious modifications. You have multiple edges. You could list a vertex twice to represent two edges and so forth, but usually we're not going to use the adjacency list. We're more likely going to use the adjacency matrix. A matrix is simply a rectangular array of numbers, and the example I've given you here has a size 2 by 3, where the 2 represents the number of rows. Those are the horizontal, and so those are the 2 rows that I've circled there. And then it has 3 columns, 1, 2, 3 columns, like so. So he lists the number of rows first, the number of columns second. And we use this notation Aij to indicate the thing in row I, the number in row I, and column J, counting from the upper left-hand corner. So A12 would be the object in row 1, column 2. That's that guy right there. Yep. Right, so we make up a matrix for a graph in the following way. First of all, we'll take a graph and we'll order the vertices. They do have to be in an order to specify the matrix. So there's a first vertex, a second, and so forth, and however we list them. You can do it in whatever you like, but it has to be an order that you do specify. So we'll make a matrix that is square, n by n, where n is the number of vertices, n equals the order of G. And the entry, the ij entry in row I and column j will be the number of edges connecting vi and vj. In a digraph, it will be the number of edges from vi to vj in the ij entry. So let's make a pretty quick example of one of these. And so I guess I'll do one that's a digraph here just to give you that. So an example of a digraph. Let me draw one here in black. So, whoops, that is not black. There we go. We'll draw one in black here that has maybe 4 vertices, not too many. And I'll draw one more edge in there like so, and we'll order this one like so, and that one like so, that one like so, and that one like so. I'm going to put another edge here, but I'm going to draw that one like so. And what that represents is actually 2 edges. This is really an edge that way and an edge this way. They're not multiple edges because they're pointed in different directions. But for shorthand, that's totally shorthand here that I'm using right here, shorthand, to indicate those 2 edges. So there are 2 right there. Okay, so in this case here I want to draw the adjacency matrix. So the way I'm going to do it is as follows. I'm going to take the standard order. I'll take the order A, B, C, D. That is alphabetical order because that's natural. And so our adjacency matrix will be the matrix A. And though you do not have to draw the or write the vertices along the top and the left-hand side, I do that often just for convenience in explaining what you're doing here. Those are not required as long as the order is specified, so you know what things refer to. So A is not connected to itself. I'll put a 0. There's no edge from A to A. No loop, in other words. A does not point towards anything but D. So there's one edge point. Oh, sorry, I forgot myself there. It does have an edge. This guy right here says there is an edge also to B. B points to A and D. C points to B and D. Oh, yeah, so 0 to A, but 1 to B, points to B, has an arrow to P, not to itself, and then 1 to D. That's where these are coming from. D has nothing pointed anywhere. So that would be 0 all the way across, which is kind of interesting. It does have edges, but they're all pointed into it right there, right? So that's the situation we have right there, and you can actually see from this how many edges there are. There's 6. If you just count the line segments, there's only 5, but remember this one up here has got an edge in each direction. Okay, so let's do a couple more examples. You can do a adjacency matrix for this graph, and this one is undirected graph. And so if we do the matrix for this, and I'll give it a name, call it A. And here we've got RSTUV going around just using the alphabetical order. So I'll do this fairly quickly. So R connects to U and V. S connects to T and V. T connects to S and U and V. No loops there. U connects to R and T and V. And V connects to all the other 4. So it connects to everything but itself. Now, one thing you'll notice about this matrix is that it is symmetric. Yeah, that is to say, if you look at, I'm just drawing through this, not exiting out, but that's your line of symmetry there. Then it's symmetric with respect to that line. Another way to put it is that, if I take that out again now, if you look at a particular column, that's the same as that row there, right? So it's symmetric. That's for an undirected graph. It will always be symmetric. For the directed graph we did above, it did not display that symmetry. Not symmetric. Now it could be, but in general it wouldn't be. What would mean that it's symmetric would be that each edge would have to have a counterpart that pointed in the opposite direction. So here's one to sketch a graph that has that adjacency matrix, and A, B, C, D, E. That has 5 vertices, so I'll go ahead and do that, and we'll put 5 vertices here. 1, 2, 3, 4, 5. A, B, C, D, E, and I don't know how they're going to be aligned out here, but if this is A, B, C, D, E, then the same A, B, C, D, E, just to help me figure this out. So A goes itself, so that's a loop, right? Let me go ahead and draw that loop there, and I'll put an A beside it like so. So that's that 1 right there, right? And then it also points to C and E. A has an edge to, whoops, C and E. Yeah, they're not directed. B has edges from, well, it has a loop also, and then it goes to C and E. C and E, and then it also has a loop there. C goes to A, we already have that. B, we already have. So really we only have to look whether it goes to D and E, and it goes to E. Oops, goes to E. D has 2 edges with E. D has 2 edges with E. And I guess I realized that I messed up on this. I meant to have it like this. That's not symmetric. So if you would just play along with me and change that. So we'd have 2 edges there. So the 2 here gives us the multiple, and it's the same thing that's over there too. So E should all be done. It has an edge to A, it has an edge to B, it has an edge to C, and it has 2 to D, but not a loop. Okay? All right, so you can sketch a digraph for this one here. We already sketched one, so I'm going to leave that for you to sketch. You'll see that it has 2 here, for example, as well, going from A, B, C, D, E, E to A, B, C, D. 2 going from E to D. Nothing is going from D anywhere, but there are edges coming into D. So there are 1, 2, 3, 4. So there are 4 edges coming into D. So the in degree of D would be 4, and the out degree of D would be 0, right? You could finish that sketch, but I think I'll go ahead and stop this here.